All right, our next topic is 3.5 task priorities. Certainly an important part related to FreeRTOS. As you know, when you call the task create, there's a priority that you pass in as the parameter, and that's used for the initial priority. And in many cases, that may be all you do. You set the initial priority and you never change it. But if you do need to change the priority, there's a task priority set, and you can actually change the priority of the task. As far as the number of priority levels, there's a config max priorities that is in the configuration file, and it has the maximum number of priorities. Priority 0 is always the lowest, so keep that in mind. That's always the lowest, and then config max priorities -1 will always be the maximum priority. Now the scheduler, based on these priorities and based on the number of tasks that you have to run, it has some options. So option 1 is you can have this config use port optimized task selection set to 0. And if you have that, it uses generic C code to do your task selection. That is, it's going to pick the next task to run using some generic C code. Option 2, if you have config use port optimized task selection set to 1. In other words, you're saying take advantage on this particular port to optimize the task selection. This is actually faster than the generic method. And the downside of this is it uses a port optimized assembly code. I say the downside, but the downside is it's harder for you to follow and understand assembly code, although certainly not impossible. And of course the good thing is it is highly optimized for this particular port, and it will make it the fastest way to pick the next task to run. If you choose to use this one, config max priorities cannot be greater than 32. So basically you have up to 32 different priorities, and all ports do not have this as an option. So it's something you can check in your configuration file and see whether you have this as an option or not. Importantly, the scheduler always runs the highest priority task. So it's always picking the highest priority task. So if 2 or more tasks are at the same priority and they're both ready to run, then the scheduler is always going to run the one that's in the higher priority. And basically the way it transitions from one to the other, it'll take one task out of the running state and put the other one into the running state. Let's talk a little bit about tick time measurement and tick interrupts. So the way this works is there's a periodic interrupt that's used, and it enables what's called time slicing. That is, the periodic interrupt tells the system when it's time to look and see if another task should be running. At each time slice, the scheduler is going to run and see, okay, this task runs next. You actually have a configuration option, config tick rate hertz, and that sets the frequency of the timer. So how often do you want this tick to occur, where you can preempt what's running and see what needs to run next. Here's an example. Config tick rate hertz 100. That would mean every 10 milliseconds, it's going to look and see what needs to run next. Here's a diagram of what's happening. You can think of task 1 as running, right? Task 1's running, and then suddenly the tick interrupt occurs. When the tick interrupt occurs, the kernel is going to run and decide what runs next. And notice here, in this case, the kernel decided that it's time for task 2 to run. So task 2 runs. Then, boom, we get the tick interrupt again, and now the kernel decides task 1 is going to run. So the thing to observe is right here, when the tick occurs, this is when the kernel comes in, and really is when the scheduler comes in and decide who is going to run next. Now, related to the ticks and time, there's this macro called PD, which stands for the port definition, millisecond to ticks. You'll use this quite often because they're parameters you pass into some of these functions where you need to give it a time, and it's typically easier for us to work with milliseconds as opposed to ticks. So you pass in a millisecond value and it'll return to you the number of ticks. So this macro will be used quite often in our code samples. The FreeRTOS API always will specify ticks as the parameter, but we'll use this macro to convert to milliseconds. So here's an example. We may want to work with 200 milliseconds, so we pass in 200 right here. We put it into this macro PD ms to ticks of 200, and what we get back is a tick type, and this tick type would be in ticks. How many ticks of the clock do we want to go by? So here we have a code demo. We have our task function. Just like we saw earlier, a vTask function, it doesn't return anything, has one parameter passed in. In this case, we just take the parameter and we're going to print out a string. But if we look at part 2 of this demo, we see we're going to have 2 of these running tasks, and we come in, we say we're going to start task. The first task is task 1, the second task is task 2, and we now see that as these run, what's happening when you say task start scheduler, now we understand that in the background what's happening when the tick goes off, it checks and sees, does task 1 need to run or does task 2 need to run. Speaking of running or not running, let's look at section 3.7, which will expand in more detail this not running state. Up until now, we've just said you're either running or not running, which was good, right? That worked fine for what we're looking for. But this was actually a simplification. There's more to this not running. Particularly, we need to focus on what happens when we start dealing with an event-driven task. So what we mean by that, the event-driven task, an event-driven task performs work only after an event triggers it. So if there's been no event, there's nothing for it to do, so it does not take up any processor time. That's very important because you would only want to use processor time when you need to, so the task will enter the running state only when the event occurs. So the deal is, using event-driven task means these tasks can be created at different priorities without the highest priority always taking up all the time. That is, if you had the highest priority and the other lower priorities and they were all always running, then the lower priorities would be starved for time because the highest priority would always be ready to run. The way we get around this issue is we introduce what's called the blocked state. This is a subset of the not running state. So it's still not running, but to be more specific, this will be blocked. Tasks that enter the block state, there may be 3 types of events that you're waiting for in the block state. The first one could be a temporal or time-related event. That is, the event is after a delay period, an absolute times reached. So in other words, you're running, and let's say you go to sleep for say 1,000 milliseconds. Well, you're waiting for an event, and until that event, saying 1,000 milliseconds have gone by, you can be in the blocked state. Number 2, you may be waiting for an asynchronization event. That is, you've done some work and you get up to a synchronization event and you want to wait for another task to tell you that something's happened, or maybe you want to wait for an interrupt to tell you that something has happened. In any case, you'd be in the blocked state until a synchronization event occurs. And number 3, you might be waiting for both things. That is, you might be waiting for a synchronization event. However, you also want to have a time event so that if the synchronization event never occurs, instead of just hanging at that point forevermore, you could have a timeout, and that would allow you to get out for a worst case scenario get out of this blocked state. Now it turns out these kernel objects that create synchronization events is quite extensive, and as you can guess, as we go through this course, we will cover all of these in great detail in future lessons. So we'll be seeing how you can use queues for synchronization, how you can use binary semaphores and counting semaphores for synchronization. We'll be seeing how you can use mutexes and recursive mutexes for synchronization. Also, we'll introduce something called event groups and task notifications. So a lot more to come on all of this, but the key is they know how to handle synchronization, and so they'll take use of this not running state, which we call the blocked state. So not running, blocked, but there's another not running one, and this one is called suspended. Suspended state, again, is a substate of not running. The only way to get into the suspended state is someone says task suspend. You can either suspend yourself or someone else can suspend the task. And in a similar way, the only way out of this suspended state is to do task resume. So task suspend says you've got nothing else to do until someone says task resume. Although I mention these, and they're certainly important to know them, most applications do not use this suspended state, but it is there if you need it. Finally, in this not running state, there's something called the ready state. That is tasks that are in the not running state but are not blocked, they're not suspended, they're ready to run. In other words, they would run if they could, but the processor is currently executing something else and they're not yet running. So this would be the ready state. So now we've got a full state machine that defines all these states. In fact, this block diagram makes it easy to see. We've got our running state, which we know on our particular STM board, we can only have one thing running at a time. And from running, we can either be ready to run and run when we can, or ready to run. Or if we're running and we're calling a blocking API, that is, maybe we're waiting for a synchronization event, then we go over here and we'll be blocked. Or let's suppose we're running over here and we call the suspended, then we get suspended. Notice if we're in the blocked state, when we do receive the event, then we could get back to the ready state. And in fact, we see the running, we're ready and then running, ready, running, ready, running, until we somehow get blocked or somehow we get suspended. In fact, one of the best ways to demonstrate going into the blocked state is using this task delay. So when you call vTask delay, you give it how many ticks you want to delay, and this is the classic way to put yourself into the blocked state. This would be a temporal or time-based time of being in the blocked state. And again, we can use this PD ms to ticks macro to set to what the tick delay should be. So here's a code demo using this vTask delay. We have our function, this will be the task, so vTask function, have a parameter passed into here. Notice early in the function, we say we want to delay 250 milliseconds, so we use the PD ms to ticks, and that gives us this variable which is of type tick type. It's going to be x delay 250 milliseconds. We come in here, one of the parameters we take is our task name, and then we print out our task name, and then we delay, in this case, 250 milliseconds. So the idea is we delay 250 milliseconds, print our name, delay, print our name, delay, and so forth. Now there's also something called an idle task, and the idle task is actually created automatically when the scheduler started. You can consider you get this idle task for free, and so there's going to always be at least one task in the ready state at all times. In other words, if there's nothing else to do, certainly the idle task can do something. Here's a block diagram of that. So as we're running, let's say we've got task 2 that's running, and then the scheduler decides that task 1 is going to run, And then we see when there's nothing else to do, this idle task is running. So idle, 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 idle. As long as there's nothing else to do, the idle task is here. But as soon as there's anything else to do, then those other tasks would run. So keep in mind, behind the scenes is this idle task. Speaking of that, not only can you delay a certain amount of time, for example 250 milliseconds, you can delay until a given point in time. So what we mean by this, we could come into this task delay until, give the previous wait time, and then give it a time increment. So you could think of this being similar to task delay, except this time delay is going to be absolute instead of relative. That is, it'll always be absolute based on this previous time, this previous wait time. The most common way to use this is to call this X task get tick count. Anytime you call this, it gives the tick count at that point in time. And so you can take where you're at that point in time and then add this absolute increment to it. And of course, that's handled by calling v task delay until. Here's a code sample related to that. We see we come into our task function. Notice right here for the last wait time, I call X task get tick count. Once I've got my tick count, when I do this task delay until, I pass in my last wait time from right here, and then I give, in this case, my millisecond to ticks of 250. Now, as I mentioned, you can also combine both blocking and non-blocking tasks. That is, here's what we'll demonstrate. You could have two tasks that are created at priority 1, and suppose they just spin in a loop and use time and they never ever enter the block state. And then suppose there's a third task at priority 2. And of course, priority 2 is going to be higher than these two tasks at priority 1. It's going to print out a string periodically, but then it's going to delay. And of course, when it delays, that'll give time for the other two tasks to run. So here on our code demo, we have this continuous processing task, and notice all this guy's going to do is to spin in a loop, constantly printing out the task name. Right? So just totally using time, printing out the name. That's the continuous processing task. The periodic task, on the other hand, for this one, notice we will come into here, we'll still print out our periodic task running, but then we're going to delay, and we're going to delay the wait time plus whatever our delay is, so in this case 3 milliseconds. When we delay, we'll enter the blocked state, and that will allow the lower priority task to run. So here's what we've got. We've got continuous would run, then continuous 2 will run, continuous will run, continuous 2 will run, and so forth, until finally it's time for periodic to run. Periodic is higher priority, so it will get the ability to run next, and when it finishes by calling this delay, it would immediately give time back to priority 1, which is ready to run, and then continuous 2 and continuous 1 and so forth. So the point is, this higher priority task, when it's ready, when its time has expired, it will definitely be able to run, and then when it hits the delay in the block state, it gives the rest of the time to the other task.